Welcome to Holyfield Physics TV. Today we're going to look at magnetic fields. This is part of the OCR Physics A2 course in the module Fields, Particles and Frontiers of Physics. We'll start by looking at the bar magnet, the field around a bar magnet, and it's the usual butterfly shape, but the important thing here is the direction of the field. And the direction of the B field is always the direction of force that an isolated north pole would feel. So in other words, the field lines flow from the North Pole to the South Pole. Looking at the flux density, this is, if you like, field strength, and as the term suggests, B is how closely packed the flux lines are. Here we've got 3 flux lines travelling through an area of 1 metre squared. So we have magnetic flux of 3 Weber, 3 field lines. And the flux density is the magnetic flux divided by the area. That gives us 3 Tesla. Stronger field, closer packed field lines, passing through the same 1 metre squared. This time we have a flux density of 5 Tesla. Looking at the magnetic field around a current carrying conductor, we get these nice circles. And to work out the direction of the field, we need to use the right-hand thumb rule. The thumb is in the direction of the current, and your fingers wrap in the direction of the field. So in this case, we have an anti-clockwise field. Here we've got the current flowing down. We get our field lines around the wire using the thumb rule. This time we have a clockwise field, but the field is always perpendicular to the current. And so sometimes it's easier to represent this with the current going directly into the paper, into the board, which is demonstrated by the X on the right hand side. And as you can see, if you point your right hand thumb into the screen, your fingers will wrap round in a clockwise direction. The other thing to notice here is that the field lines are not equally spaced. They spread out further the further we get from the current itself. So that means that the flux density, B, decreases the further from the current we go. Now if we look at current flowing upwards on the right hand side, downwards on the left hand side, we get our circular field pattern on the left hand side, and using the thumb rule, that's a clockwise field. On the right hand side, the field pattern is now an anti-clockwise. But down the centre, in the middle of the coil, the pattern combines and we get this field. Putting this together for a number of coils carrying a current, in other words a solenoid, we get a new pattern building up. And as you'll see, it's fairly straight down the centre of the coil. It's probably easier to see though if we remove the coil and the plain paper, and there's the pattern that we have. If we overlay a magnet on top of this, you'll see that the field is actually identical to a bar magnet. And what this means is that magnetically speaking, the solenoid is a bar magnet. Because it has exactly the same shaped field, it behaves in exactly the same way as a bar magnet will behave. You've been watching Holyfield Physics TV. My name's Richard Gould. Thanks a lot for watching and listening. Work hard, do well in your exams.